Suppose y varies at a constant rate of change of m with respect to x. This means that changes in x and y are proportional, which means that the ratio of the change in y to the change in x is always equal to this number m. And this means that the change in y is always m times as large as the corresponding change in x. This holds for any corresponding pair of changes in x and y. Now, let's assume that y varies at a constant rate of change with respect to x, and the constant rate of change of y with respect to x is m. We'll also assume that y equals y1 when x equals x1. So we'll sketch a graph to keep track of our quantities. So when x equals x1, we'll say x1 is right here, we know that y equals y1. So we have a reference point, x1, y1, on our graph. Now for any value of x, if we pick any value for x, we can always determine the value of y. We have enough information. So given a new value of x, we can think of x changing from this initial value x1 to the current value of x. And this change in x is always equal to the final value, this new value of x, minus the initial value, x1. Now, since we have a constant rate of change of m, the change in y is going to be m times as large as the change in x. And we know that the change in x is equal to x minus x1. So we can represent the change in y as m times x minus x1. So now we have this point right here that represents our xy pair. So this new value of y is over here on the vertical axis, and we can determine this value by thinking about starting at our initial value y1 and changing by however much y changed by. So we changed by delta y. So our new value of y is going to be equal to the change in y plus whatever our initial value of y is. So our change in y plus y1. And we know that our change in y is equal to m times x minus x1, and then we add on our initial value of y. So this tells us that, if we rewrite this, this tells us that y is equal to m times x minus x1 plus y1. And this works for any constant rate of change m and any reference values for x and y. We used x1 and y1. And this form is so common that we call this the general linear function formula. So we call this form of a linear formula definition the general linear function formula. Now we know what each piece of this general linear function formula represents. So if we rewrite this, y equals m times x minus x1 plus y1, we can break this down and look at each piece individually. So the x1 represents a reference value, so a reference value for x. The x minus x1 represents the change in x from our initial value x1 to our current value of x. And when we multiply that by m, we're computing our change in y from our initial value y1 to the new value of y. Then if we add to our change in y the initial value of y, we end up with the new value of y. So each piece in this general linear function formula has a lot of meaning. So let's look at an example of a linear function formula with some specific numbers. So let's assume x and y vary together such that y equals 2 times x minus 5 plus 1. Now we recognize this as the general linear function formula, so we can identify 5 as the reference value for x. We can identify 1 as the reference value for y. And the 2 represents the constant rate of change of y with respect to x. So if we sketch a graph, we know that when x equals 5, y is equal to 1. So we have this reference point on our graph, and we can use this formula to determine the value of y for any given value of x. So for example, let's pick a value of x. So let's say x equals 3.5. We can compute the value of y using our formula. So we can compute this as 2 times x minus 5, except we know our value of x is equal to 3.5. So 2 times 3.5 minus 5 plus 1. Now we can compute the value of 3.5 minus 1. This value is equal to negative 1.5. And this negative 1.5 represents our change in x. So if we start at an x value of 5 and end at x equals 3.5, this negative 1.5 represents the change in x. Now when we multiply negative 1.5 by 2, that's equal to negative 3. And this negative 3 represents the corresponding change in y. Then, when we add negative 3 and 1, we get negative 2. And this negative 2 represents our new y value. So it represents the value of y when x equals 3.5. And we can do this for any value of x. So we can imagine x varying and engage in this way of thinking. So let's see what happens if we imagine x varying and tracing this point that results from coordinating x and y. Now if we let x and y vary, we coordinate the change in x and the change in y in this new point, what we get is a graph that happens to be a line. So the graph relating x and y ends up being a line.